Today's lesson is going to be focusing on continuity. You've heard me talk a little bit in the past regarding some functions, like polynomial functions, are continuous functions. And what that means is that they are continuous at every single point in their domain. Okay, so that's kind of the formal piece to this, but continuity at a point C, which is just an x value, there's actually, this definition actually requires three things. One, f of C is defined. In other words, C is an x value in the domain, which means it has a y value. There is a y value paired with the x value or C value. The second part of this definition is that the limit of the function as x approaches C has to exist. And then the third part of this is that the limit of the function as x approaches C has to equal f of C. So parts 1 and parts 2 have to have the same value for continuity, for a function to be continuous at a point. Okay, so remember, I'll just put this here. F of C equals a specific y value. In order for a limit to exist, the left-hand limit must equal the right-hand limit, and then this is number 1 has to equal number 2. So when we're talking about continuity at a point, these are the things that we have to consider, and in answering questions about continuity, we have to refer to these three things. So let me slide this up. If we look at the graph here that I've provided, this particular function is definitely a broken graph. It has the graph is broken. There's holes in the graph. There's just, the domain starts with 1 and ends at 4, but doesn't have, well, it has values at all of the x values, but this function is not continuous at x equals 1 or x equals 2. So the function is discontinuous at x equals 1 and x equals 2. So notice that at x equals 1, the left-hand limit is 0 and the right-hand limit is 1. So at x equals 1, the function is not continuous. Same thing is true at 2. The left-hand limit is 1. The right-hand limit is 1. F of 2 exists, but the limit as x approaches 2 is not the same as f of 2. So therefore, these are the two values where this function is not continuous. Let's talk about this one. And I'm just wanting to determine for both of these, identify the points of discontinuity. So this function is, the function is discontinuous at, I'm going left to right, so at x equals -3, at x equals -1, it's continuous at all of these, and then at +1, okay? Continuous, 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 and then, so 4 is really not, I'm going to go ahead and say 4. But endpoints are a little tricky. And the only reason why I've included 4 is because the left-hand limit is equal to -1, but f of 4 equals 1. So anyway, notice that what if I were to ask you about at x equals, let's say 2.5. What about at x equals 2.5? Is this function continuous at x equals 2.5? Well, over 2.5, you have a point right there. So, number 1, what is f of 2.5? And we'll just give it a good estimate as to be 0.5. The second part, does the limit exist as x approaches 2.5? Does the limit exist? Yes, and it is 2.5. And number 3, does the limit of the function as x approaches 2.5 equal f of 2.5? And the answer is yes, they both equal, wait a minute, that's not 2.5, that's 0.5, sorry. And they both equal 0.5. So this particular function, I just picked a value of 2.5 at 2.5. F of 2.5 is about a half. The limit of the function as x approaches 2.5 from the left and from the right is also 0.5. And because these two are the same, the limit of the function as x approaches 2.5 is equal to f of 2.5, which equals 0.5. And so I wanted to use a point where the function was continuous as well. So now on the next one, the next example, it says explain why the function below is not continuous at x equals -8. So at -8, there's x equals -8. Okay. Does f of -8 exist? Yes, there is a point at the x value of -8, and it's like -3. Does the limit as x approaches -8 exist? And the limit, the left-hand limit as x approaches -8 is -6. The right-hand limit also exists, and they're both -6. But the function, or since the limit of the function as x approaches -8 does not equal the limit as x, no, that's not right, does not equal f of -8, f is not continuous at x equals -8. So I answered or it didn't say answer, but it's explain why the function below is not continuous. Well, this function is defined at -8, and the limit exists as x approaches -8. But since the limit as x approaches -8 does not equal f of -8, since those two are not the same, f is not continuous at x equals -8. So in calculus, there's a lot of explaining mathematically why something is or is not. Okay, so now let's look at another example. Okay, so looking at, I guess it's page 2. Here we have a piecewise function, and I want us to find the following. Does the limit of this function exist as x approaches -2? Okay, so where's -2? Here's -2. Does the limit exist? And the answer is yes, because the left-hand limit is 1 and the right-hand limit is 1. Okay, so now what about f of -2? Well, f of -2 is going to be the actual point there, which is 1. And so the question is f continuous at x equals -2? And explain. So the answer is yes. F is continuous at x equals -2 because, so see here you're answering the question, yes, because, and you state that the limit of f of x as x approaches -2 equals f of -2, which equals that value of 1. And this is so very important, this is your reason why you know that this function is continuous at x equals -2. Okay? So what if we have, so what if I have this little piecewise function right here? Let's take a look at this. This piecewise function is in the form of an equation. And I'm gonna just we're gonna jump ahead a little bit, but I wanted to use this because it's a piecewise function. How can we find limits algebraically? How can we find limits algebraically? Well, here we have this piecewise function, and I want to find the limit of this function as x approaches 2 from the left. Okay, well, this piecewise function, the top piece is defined for the x's that are less than 2, which would be to the left of 2. So the cool thing is I can do just a little substitution. 2 squared minus 4 times 2 plus 5. So the limit of this function as x approaches 2 from the left will be 4 minus 8, which is -4. -4 plus 5 is equal to 1. What about finding the limit of this function as x approaches 2 from the right? Well, the values that are greater than 2 are to the right of 2. So all I have to do is I simply can substitute 4 or 2 for x to give me 4 minus 2, which is 2. So the left-hand limit is 1. The right-hand limit is 2. Therefore, the limit of f of x as x approaches 2 does not exist. And f of 2, which piece do we use there? Since 2 is included for the bottom piece, I would get 4 minus 2, which equals 2. And to answer the ultimate question, is f of x continuous at x equals 2? The answer is no. F is not continuous because. Okay, so let's think about those 3 reasons. The first reason, let's think about those 3 conditions. Is f of 2 defined? Yes. And the second part to that definition is, does the limit exist? And so, no, f is not continuous because the limit of f of x as x approaches 2 from the left does not equal the limit of f of x as x approaches 2 from the right. Here you are saying that the limit does not exist, and you're saying that the reason why it doesn't exist is because the left-hand limit and the right-hand limit are not the same. So when you're explaining, you have to be very descriptive. So we've talked a little bit about continuity and discontinuity. And on these examples, we're focusing on continuity at x equals 0. X equals 0, x equals 0, so on. So at x equals 0 here, this is a terrible picture, but this function at x equals 0 is continuous. You have f of 0 is defined, and the left-hand and the right-hand limit are also defined. They exist, therefore, and they are the same, so therefore the function is continuous. Now let's talk about the next example. There is an open circle here that's hard to see. You have this line that has a hole in it. At x equals c, the function is not continuous. It is discontinuous. And we call that a removable discontinuity because it really looks like somebody has reached into the graph, plucked out a point, and removed it. So we call that a removable discontinuity. On the next example, it's very similar to this one. We still have this open circle, but now we have this closed point there. So this is also considered a removable discontinuity at x equals 0 because in this one, it looks like somebody's plucked the point out and then put it above it and removed it. Removed the point and just placed it above it. So these are two different types of removable discontinuity. Basically, removable occurs when there's a hole in a graph. Now let's talk about jump discontinuity. Jump discontinuity, and again, this is so hard to see. We're going to say that this is an open circle and this is a closed circle. This is jump discontinuity because it looks like you're traveling along the graph, and to go from this piece to this piece, you have to jump from here to here. But the real reason that this is called jump discontinuity is because the limit of this function as x approaches 0 from the left equals, I'm going to say L for left-hand limit, and the limit of the function as x approaches 0 from the right equals a right-hand limit. They're two different values. We have infinite discontinuity. Here we have these little branches. They should have arrows, and you'll notice that there is a vertical asymptote between those two branches. So as you come in from the left, your graph shoots upward. As you come in from the right, your graph shoots upward. And when I say coming in, I'm talking about coming into 0. Your left-hand limit is infinity, and your right-hand limit is infinity. And the function is discontinuous there. So, but there's infinite discontinuity there. And then here, we say that this is oscillating discontinuity at x equals 0 because the graph, as you come in from the right and from the left, the graph is just bouncing back and forth between two y values. So those are some different types of continuity. Excuse me, those are some different types of discontinuity. And so we will wrap up this video, and we'll look in our next video, we'll talk about the intermediate value theorem.